Good afternoon, ladies and gentlemen. I'm Bosh from National Tsinghua University, and I'm here to share with you the impact of temperature gradient on the growth of intermetallic compound in solid copper-indium copper systems. And my advisor is Professor Fang Yang. With the development of the advanced packaging technology, the microbump technology is adopted with a diameter of around 10 micrometer. In the simulation results at the right-hand side, this bump suffers with a large temperature difference during the device works. When the bump size is shrinking in the future and also increase the transistor density, at the same time, the diameter of the bumps decrease, and therefore, we will see the solid joints will undertake a higher temperature gradient in the near future. And this comes to a reliability issue called smoke migration. The joint force can be expressed in this formula, Q star over temperature and times the temperature gradient. And the Q star here means the heat of transport. It can be either positive or negative, indicating the direction of atom migration caused by temperature gradient. In the previous study, people found out that copper, nickel tends to move toward the cold end, and tin tends to migrate toward hard end. We can clearly see in this nickel-tin-nickel solid joint. At the cold end, there was a thick nickel-tin IMC formed at the interface at the cold end, and there were a heavy UBM consumption at the hard end. And this kind of asymmetrical IMC growth is a typical smoke migration failure phenomenon. In this study, we try to replace tin solder bump with indium with two reasons. First, indium has a relative low melting points than tin, which is lower nearly 80 degrees, and this can help us to achieve a lower temperature bonding temperature, which can reduce the thermal issue at the processing. Second, indium has a better thermal conductivity and electrical resistivity, and also which makes indium has been used for a tin material as an industry. Before we start the project, we found some papers were highly related to our work. Our lab has studied on the nickel-indium systems before, and nickel is one of the most common UBM and the solid indium system. And we found that there were only one IMC phase formed after aging test, nickel 3 indium 7 phase. And we also can observe that there were no conductor void formed at the interface. The other team, led by Professor Gao, they have studied about the copper-indium systems. However, there were multiple IMC at the copper-indium phase in the phase diagram. What's interesting is that there is a predatory reaction happen at 107.5 degrees Celsius, which this copper 11 indium 9 phase transform into copper indium 2 phase. The other lab, led by Professor Shen, also work on the copper indium systems, especially at the smoke migration behavior of the molten indium. There were a very thick IMC growth at the cold end, but a pretty thin IMC at the hard end. In addition, they have calculated the DQ star value in this paper. With this paper reviews above, we are wondering the reaction of copper and solid indium systems under a temperature gradient. This can help us know better about the lifetime of the solder joint. We fabricated a symmetrical copper-indium copper sandwich structure with copper in 4 micrometer and indium in 30 micrometer. The specimens were then put on the hard end and reflow at 220 degrees for 2 minutes. The X-ray image shows there is a symmetric structure with copper, IMC, and indium, IMC, copper. With the EPMA analysis, we can identify these IMC were copper indium 2, and copper 11 indium 9 phase. And then we put this sample after reflow, and we then put into two groups. One with given a temperature gradient with hard end at 150 degrees, and a 30-degree eddy cold end. The other group was put in an isothermal aging oven at 80-degree and 100-degree. All these samples were done in situ observation at 0, 600, 1200, and 1800 hours. Here is a simulation of a small migration test. Due to the scale is too small for us to detect the actual temperature. We can see the result here. At the hard end, in the Indian foil has a 95.9 degrees Celsius, and it was 84.2 degrees Celsius at the cold end. The average temperature of the Indian is about 10.9 degrees Celsius, which can calculate the temperature gradient into nearly 2000 degrees Celsius per centimeter. And also, we set the isothermal oven as 100 degree, which is close to 95 degree here, and 80 degree to close at the cold end temperature. Let's focus on the sample which under a temperature gradient first. The upper image are the hard end of a sample, and we observe in the same area to observe the microstructural evolution and the phase composition transformation. From the in situ backscatter ACN image, the IMC grew thicker as the time increased. In addition, void forms at the copper layer could be found in at 600 hours at the hard end and 1200 hours at the cold end. We can also observe there were some phase contrast at the IMC, which inspire us to utilize EPMA to define the composition. The color in EPMA result stands for the intensity, red stands for the highest intensity, and blue stands for the lowest intensity. And copper and Indian signal were separated to discuss in detail. We can see that there was a pure copper layer after reflow process in both hard end and cold end. When it comes to 600 hours, some Indian diffused into copper layer in both ends, and after 1800 hours, copper layer was almost as hot at both ends. For Indian, we can see there were two different compositions of IMC with a green one and a yellow one. And after the reflow process, when the time increased, the profile transformed into a big green area, showing that there were a phase transformation happened here. With the point measurement, there were copper 11 Indian 9 and copper 11 Indian 2 phase after at the hard end after 600 hours, and copper 11 Indian 9, copper Indian, and copper Indian 2 phase at the cold end. For B spot here at the hard end, we can see that there was a 77% of copper. We guess that might be this atomic ratio is between pure copper and copper 11 Indian 9. We guess that there might be a pure copper layer and some small copper 11 Indian 9 grain captured at the same time. And the same idea is also works on the C spot at the cold end here. After 1800 hours, there was still copper 11 Indian 9 and copper Indian 2 phase at the hard end, but only copper 11 Indian 9 with different composition at the cold end. It seems that there was atomic flux migration causing the difference of the IMC composition. We then measure the thickness change of both IMC and copper layer to discuss the thermal migration behavior. It's interesting that the IMC thickness of both hard end and cold end are close at each time spot. However, the remaining copper thickness shows something different. The copper layer at the hard end consumed dramatically after 600 hours, which means there were a copper atom dissolved at the hard end and migrated toward the cold end, so that there was a less copper consumption at the cold end. In a classical thermal migration results, the IMC at the cold end at this time will grow even thicker. Nevertheless, the IMC at the cold end did not grow thicker in this case. We guess this is due to the Indian atoms were also migrated toward hard end at the same time, so that the IMC thickness of both sides will be equal. We try to discover the critical temperature gradient of these systems to clarify the driving force is large enough. According to Kinning 2 and Professor Kinning 2 and Chi Chen's study, the energy of atom to migrate in electron migration and thermal migration are similar, so that we can make a simple consumption. From electron migration mechanism, the work done by driving force can be expressed in this way, and the thermal energy change are known as 3k delta T here. These two terms are equal if both electron migration and thermal migration can happen. Therefore, we can get this formula divided by delta x in two sides, so the critical temperature gradient can be expressed in this way. And then we found a paper to support the EM parameter of indium in indium matrix, which is in this table. However, there was no paper found about electron migration in copper indium systems. So we use a number in copper tin systems to get a closer answer. The critical temperature gradient of indium and copper are 583 degrees Celsius per centimeter and 401 degree per centimeter. And the temperature we set up in this test is nearly 2000 degrees Celsius per centimeter, which is a lot higher than the theoretical value we calculate. To sum up, the temperature gradient in our case is large enough to trigger thermal migration. The reason that there is no big difference between the IMC thickness is due to the competition of both indium and copper flux. To clarify the effect of temperature gradient, we also did an isothermal experiment. At 100 degrees, the copper film formed void after 600 hours, indicating a rapid reaction rate between copper and indium, and then the copper layer keep remain after at 1800 hours. And also you can see that it seems that there are no phase contrast between the IMC. At 80 degrees, however, the remaining copper layer was higher than that of the 100 degrees, and the void formed after 1800 hours. It should be noticed that there seems to be different phases of IMCs formed at 80 degrees. In addition, the IMC morphology after reverse showed no big difference between times, neither 100 degrees and 80 degrees. Compared to the result of the TM test, it's obvious that there is a less indium signal in copper layer at both sides in different reaction time. At 100 degrees from the indium signal, it seems that there are a different composition of the IMC at 0 and 600 hours, but then transform into a single phase after 1800 hours. At 80 degrees, the IMC also shows multi-phase at 600 hours and remain at 1800 hours. With the help of point measurement, there were copper indium and copper 11 indium 9 at 100 degrees after 600 hours, but fully transformed into copper 11 indium 9 phase at 1800 hours. At 80 degrees, there are 3 IMC phases: copper indium 2, copper indium, copper 11 indium 9 phase formed at 600 hours, and the IMC transformed into copper 11 indium 9 and copper indium 2 phase after 1800 hours, with copper UBM remaining at both sides. After refill, the IMC grew thicker and formed copper indium phase initially, and transformed into copper 11 indium 9, which has a larger density, causing the thickness of IMC slightly decrease and consume more copper film. We guess the concentration of copper in this system is nearly equilibrium, so that we cannot find dramatically growth of the IMC at the following stage. We try to explain why there are phases with 77% of copper. In our EPMA result, we utilized FIB to achieve a stress-free cross-sectional image. When we see we can see a clear morphology of the IMC here. Surprisingly, there are lots of phases observed at the copper layer, showing that there are some tiny IMC phase growth, or maybe it's caused by the indium penetrating through the IMC. causing there is no copper indium phase at the phase diagram, and also the atomic ratio is close to copper 11 indium phase. We fabricate TEM samples at the interface between copper and IMC here for further phase identification. Since our fab is without cryo stage and there are different melting rate between pure indium and the IMC, there are void forms in our TN samples, and we believe they are maybe indium or indium rich phase. And this distribution this void distribution is also matched with the FIB result here with some bright phase here. With the help of SAD pattern, we can define that there are both copper indium phase and copper 11 indium phase at the IMC after reflow process. To sum up, two groups are set up in this study, one with temperature gradient, and this gradient is proved to drive the thermal migration test. Another team is with agent test, and the temperature setup is close to the temperature at each end during thermal migration. After reflow process, we found copper 11 indium 9, copper indium 2 phase, both happen in both sides of the samples. We then made this sample undergo the in situ observation. With a temperature gradient, thermal migration of both indium and copper atoms happened. The indium flux seems to migrate toward harden and cause the indium rich phase observed at the harden, and copper flux migrated toward cold and means there is a copper rich phase. For agent test, the case is much more simple. At 100 degrees, all IMC transform into copper 11 indium 9 phase finally. For 80 degrees, due to the low diffusivity rate, only the metastable copper indium phase transform into copper 11 indium 9 without further phase transformation. And here will be the conclusion part. Under a temperature gradient of nearly 2000 degrees per centimeter, which is large enough to trigger thermal migration, the thickness of copper indium IMC at hardened and cold is nearly symmetrical. However, composition of these IMCs are different. Temperature gradient induced directional diffusion of indium to the hardened and the copper toward the cold. Copper UBM consumption and IMC growth rate under temperature gradient are faster than that of the isothermal agent, which may cause serious reliability issues under thermal migration. We thank for the National Science and Technology Council for financial support, and I thank for your attention.